Okay, well, thank you very much for the invitation. This is a work in progress with Esther Banaian. First of all, I wanted to talk about triangulation of surface with orbifolds. So in this case, we are considering a compact surface, a finite set of marked points, but in the boundary. So we don't have marked points in the interior. And we are considering as well a finite set of orbifold points, in this case of order 3. So in these kinds of surfaces, we can define as usual arcs. So in this case is any curve whose ending points are the marked points. We don't have arcs with self-intersections. And in this case, we ask that the arc is not homotopic in the complement of the orbifolds to the boundary component or to a point. So for example, in this case, we can have an arc like this, or something like this, or maybe something like this. And a triangulation, as usual, is going to be a maximal collection of arcs that do not cross each other. So, for example, if we consider the same surface as before, we can have these triangulations. And if we look at this triangulation, we can observe a few things. For example, what we can observe is that each orbifold point, which is drawing like a cross, is surrounded by this arc, which we call bending arc. We can observe that the triangulation is cutting the surface into pieces of the following type. So we have like regular triangles, like this one. Of course, the boundary arcs might be, the arcs might be boundary arcs. We have as well things like this or like this. And we can observe as well that in some way we are going to have two elements in the triangulations, triangles and bending arcs, and we are going to use that observation to construct an algebra. And as usual, what we're going to do is to construct a quiver and a potential. The quiver is as follows. Basically, given a triangulation T, the vertices of the quiver are given in bijection with the arcs of the triangulation. And we are going to have an arrow from I to J if J follows I in the clockwise order, like this. And in this case, for the bending arcs, we are going to have loops like this. And in our case, the potential is given by the sum of the three cycles appearing in the internal triangles, plus this expression, which are the loops to the cube, one for each bending arc. Just a comment, this definition was given by Lapartine, Fragoso, and Velasco for polygons, and recently by Lapartine, Fragoso, and Moore for general algebras. Lapartine, Fragoso, and Moore also proved that if we consider the Jacobian algebra of this quiver and potential, so basically we consider the same quiver and the relations are given by the cyclic derivative of this potential, what we can have is a gentle algebra. And the important part of this is that each indecomposable object is given by strings and bands. So basically we have like a combinatorial description of the models, and we can have like a lot of information just with combinatorics. Okay, so I want to show you an example. I'm considering again the same triangulation at the beginning. And in this case, if we consider the quiver, so again, we are going to have one vertex to each arc in the triangulation, and then we are going to have arcs, arrows in this way, and we are going to have loops surrounding the orbifold points. An important thing about these kinds of algebras is that we need to consider algebras over fields whose characteristic is different for tree. Otherwise, the relations that we need to get an gentle algebra disappear. Okay, so in this case, the relations, if we compute the cyclic derivatives and everything, what we are going to have is that we are going to have these relations and these particular ones. Okay, so and what we want to do is to compute Caldero-Chapoton functions for these kinds of algebras. So a Caldero-Chapoton map is basically a map from the objects of some category to this ring. This map was defined at first for cluster algebras, for cluster categories of thinking type in 2006 for Caldero-Chapoton, but lately many generalization appears. For example, it's possible to define Caldero-Chapoton maps for categories who are Tucala-Villao and who has cluster tilting objects. That was defined by Palu in 2009, and Hahn and Jorgensen defined this similar function for categories who has just Serre function. And Cerulli, Lebartini, Fragoso, and Schuet defined Caldero-Chapoton maps for what they call decorated representation, which are basically a pair of such that the first element is a representation of this algebra, and the second element is set of vector spaces. And the expression in the last case, but in this case I'm considering like a trivial representation, is given by this expression. So in this expression, we need to consider the G vector of the model, which is given by the injected presentation. We need to consider the variety of the subrepresentation of M with the dimension vector E. And we need to consider as well the agency matrix of the quiver. Okay, and what we want to do is to relate that expression with a snake graph of orbifolds. So the snake graph was defined by Musiker, Schiffer, and Williams to prove positive conjecture for cluster algebras from surfaces. And in 2020, Banaian and Kelly defined this similar combinatorial construction for orbifolds. However, if we consider orbifold points of order 3, the definition is simpler. And in this case, we need to consider basically like the usual definition plus 3 cases. So we need to consider like these 3 particular cases. And in this case, we can observe that our arc is crossing twice tau. So in our snake graph, we are going to have tau twice. So basically, the snake graph in this case are defined by gluing together the usual tiles plus these spatial pieces. I want to show you an example. So we are considering this surface and this arc, and this part of the arc is given by this part of the tile. This other part is given by by this part, and the last part is given by this one. So basically it's the same, just we need to consider each piece like separated and then glue it together. Okay, finally, our theorem is that if we consider any arc in the surface, and if we consider the string model associated to that arc, we can prove that a CC map, the Caldero-Chapoton map of that model, is basically given by this expression in which we are considering the monomial given by the crossing of gamma with T. We need to consider this product of weights of all the edges of the perfect matching of the snake graph, and this high monomial of the perfect match. So in some ways, we have 2 different ways to compute the Caldero-Chapoton map. The one is given like in the representation part of the story, and the other part is given by snake graph. Thank you very much.